All right. So I wanted to take a moment to go through some of the WebAssign exercises just to sort of give us, well, this is what I was planning on doing during the last 10 minutes of class today, and I didn't realize that I apparently was off by 10 minutes in when I was anticipating the class being over. So let me offer that 10 minutes to you here. Um, I'm just looking at the WebAssign from section 5.1, and then we'll also take a look at what's from 5.2. We've sort of seen the ideas related to these topics in our course to this point. So this first one is asking us to look at this function 2 over x and to estimate the area under the graph and the x-axis between x equals 1 and x equals 2. We're going to use 4 approximating rectangles and right endpoints. So it's a lot of information, but if you parse it all, you can see that between 1 and 2, if you broke into 4 individual sub intervals, you'd go from 1 to 1.25, from 1.25 to 1.5, from 1.5 to 1.75, and then from 1.75 to 2. In fact, not even knowing which sketch down below is accurate. If you just look at the domain, you can sort of really feel that out in a visual sense. 1, 1.25, 1.5, 1.75, and then 2. Now, if we're using right endpoints, we would be determining the height of our rectangles by the function values at 1.25, 1.5, 1.75, and 2. Because our first subinterval is between 1 and 1.25, choose the right endpoint of that subinterval. In fact, choose the right endpoint of every subinterval. The sample points would be 1.25, 1.5, 1.75, and 2. The heights of our rectangles would correspondingly be f of 1.25, f of 1.5, f of 1.75, and f of 2. Incidentally, the width of each of our rectangles is just, well, our entire domain divided by 4, which is 0.25 in each case. So we've got 4 rectangles, each of width 0.25, each of height determined by the function f of x equals 2 over x, evaluated at 1.25, 1.5, 1.75, and 2. Actually, as I'm drawing over this picture here in the top left, this sketch looks like it's exactly correct, assuming that this is indeed the shape of our function, which I think it may be. F of 1 would be 2 divided by 1, and f of 2 would be, yeah, it looks pretty good. This should be our right sum. In contrast, over here, we would have a left sum. This is using the left endpoints. Oh boy, and I'm not even sure what this is because that's not going between the function and the horizontal axis. So, okay, right, overestimate or underestimate. Well, taking a look at our picture, we can see that our rectangles are encompassing less area than is under our curve. These little triangles of white space would be the evidence of our underestimate. Whereas if we were doing a left sum, these rectangles that protrude, that would be an overestimate. Oh, yeah, incidentally, hey, look, repeat using left endpoint. So right on cue, there's our left endpoint picture, and that would be an overestimate because these little triangular, darkly shaded regions would be where we would overestimate. Right, now this situation here is giving us the data that is our function evaluations without actually giving us the explicit function, which is actually helpful, right? Because you know what f of 0.5 is, it's 6.2, and you know what f of 1 is, it's 10.8. And now what are we supposed to do here? Find the lower and upper estimates. Ooh, lower and upper estimates. So we may not have talked about that specific topic in class, but it's worth mentioning here. Lower estimate means on every subinterval, so the subinterval between 0 and 0.5 and 0.5 and 1, on every subinterval, pick the smaller of the two function values at the endpoints. And so when you've got the 0 and the 0.5, pick the lowest function value you have access to if you want to do a lower estimate. So the lower estimate should necessarily underestimate the area under the function's graph, whereas the upper estimate should necessarily overestimate the area under the function's graph. So to do a lower estimate, it looks like based upon this data, because the velocities here are increasing as we go to the right, if we did a left sum, that would give us our lower estimate in this case because the left function value from any pair of adjacent function values is going to give us the lower of the two, whereas the upper estimate would be a right sum because take any two adjacent function values, the right of the two is going to give us the taller rectangle, which would give us more of the upper estimate. Right, with this guy here, We've got this x between 0 and 5. So we know for sure, boy, I'm not an expert with this thing, but we know for sure 5 over n is coming in as the width of our rectangle. And then what's our other piece? Our other piece is, I'll just write it in here, f of 0 plus 5i over n. So let me write it in here, 5i over n. Now you say, oh, but WebAssign's not going to take that. Well, I realize WebAssign's not going to take that because we actually have to evaluate with f. But all we have to do then is take 0 plus 5i over n and plug it in for f. Incidentally, 0 has no effect to our sum, and so we just really want to plug in 5i over n. So what's that going to be? 5i over n squared, and then 5 over n squared, and then e raised to the 5i over n. So that's maybe a little bit obnoxious to have to write, but well, that's what the f of 5i over n would equal. And so to the right of our 5 over n is our function heights, the height of each rectangle, and to the left is our width of each rectangle, and that would give us the appropriate value. Looking at this here, it looks like the function is x to the sixth, so we're one of these two. And actually, this is doing the exact same thing that we saw above. This is what we talked about in our Q&A today. If you view this I over n as 0 plus I over n, now you can see the form that we're familiar with. Here now, see, this is subtle, right? Because you almost makes you want to think that one of the endpoints is 1, but the 1 can also be a part of the function itself. So the 5 over n is constant. That does not depend on I. The 5 over n is going to be the width of each of our rectangles. We now know we're on an interval of width 5. And actually, hell, at that point, looking at the intervals that they gave us, these intervals of width 10 are necessarily out. So now we have to focus on the intervals of width 5. And focusing on the intervals of width 5, our function is going to be square root of 1 plus 1 plus x. This is the x that we're plugging in, the 5i over n. And so, I mean, technically, this 5i over n could be in parentheses as a 0 plus 5i over n, which would be indicative of the fact that our left endpoint is 0. So that's why we wouldn't see the 0 here. But yeah, if I was writing this to be very salient, make it exceptionally clear to the eye, what is going on here, I would probably write 1 plus and then put in parentheses 0 plus 5i over n. So the 0 would cue the left endpoint. The 5 is cueing the width of the interval. And then incidentally here, what the function is 1 plus x, essentially. You get out what you plug in. And so that puts us down here for the correct answer. Okay, let me go ahead